Welcome to this coding problem walkthrough. Today, we'll be tackling LeetCode problem number 722, remove comments. This is a great example of a string parsing problem that requires careful handling of edge cases. Let's dive in and explore the solution step by step. In this problem, we are tasked with writing a program that removes comments from a given source code. The source code is provided as a list of strings, where each string represents one line of code. Our goal is to process each line of this code and eliminate any comments based on specific rules. First, there are line comments, which start with double slashes, //. Any text that appears to the right of // in the same line should be ignored. Second, we have block comments, which begin with / and end with */. These comments can span across multiple lines, and all the text within this range, including the // and */, must be ignored. It's important to note that block comments do not nest. Finally, any text that is not part of a comment should remain in the output. The result should be a cleaned-up version of the source code, returned as a list of strings, with each string representing a line of code. Additionally, trailing empty lines in the output should be removed. The input to our program is a list of strings, where each string represents one line of the source code. The output will also be a list of strings, representing the source code after all comments have been removed. Let's look at an example. Suppose the input is a list of lines, starting with int main, followed by a line with a comment starting with //, and then additional code such as int a equals 1, containing a block comment. The output will include only the lines of code without comments. In this case, the line with the // comment will be ignored entirely. For the line containing the block comment, only the non-comment portion, int a equals 1, will be retained. The cleaned output will consist of the lines of code, int main, int a equals 1, return 0, end. Now, looking further into the example, we see that the block comment /*, this is a block comment */ is completely ignored. The output retains only the valid code, which is int a equals 1. Similarly, other lines like return 0 and the closing bracket remain untouched since they do not contain any comments. In another example, consider a situation where a block comment spans multiple lines. For instance, the input contains int a equals 0, /** block start, followed by the lines block middle and block end */ int b equals 1. In this case, all the text between /* and */ is removed, including the entire second and third lines. What remains is the valid code, int a equals 0, int b equals 1. This cleaned up result is returned as a single line in the output. In a different scenario, the entire input might consist of a block comment. For example, the input contains /* start of block comment, followed by still and block comment, and finally end of block comment */. Here, since all lines are part of the block comment, no valid code remains. As a result, the output will be an empty list. This highlights how the program must handle cases where no non-comment text is present in the source code. Additionally, there are constraints to keep in mind. The input will always have at least one line of code and at most 100 lines. Each line will be no longer than 80 characters and will only contain printable ASCII characters. Furthermore, it is guaranteed that every block comment will have a corresponding closing delimiter, and no line will contain both // and /*. Finally, let's consider some important edge cases. One edge case occurs when a block comment spans multiple lines, leaving no valid code in the output. Another scenario is when a single line contains both /* and */ with no valid code in between. The program should handle this by removing the entire line. Additionally, a line might have valid code followed by a line comment starting with //. In such cases, only the code before the comment should be retained. We must also account for lines that are empty or contain only whitespace. These lines should not appear in the final output unless they contain valid code. By considering these edge cases, the program can ensure it handles all possible input scenarios correctly and produces the expected output for any given source code. To address the problem of removing comments from source code, we first considered a brute force approach. This method involves iterating through the source line by line and manually parsing each character to identify comments. Specifically, we need to handle two types of comments: single-line comments that start with double slashes, and multi-line comments that begin with a slash star and end with a star slash. The steps are straightforward: traverse each line, check for single-line comments and remove everything after the double slashes, and for multi-line comments, track whether we're inside a comment block and skip all characters until the closing delimiter is found. Once the line is processed, valid code without comments is appended to the result. While this approach is simple to implement and helps in grasping the problem's fundamentals, it has significant limitations which we'll explore further. The brute force method, despite its simplicity, suffers from several drawbacks. One major issue is inefficiency, as it requires repeated string slicing and concatenation, which can be computationally expensive. Additionally, handling edge cases, such as nested comments or comments that span multiple lines, becomes increasingly difficult with this approach. These challenges lead to high time complexity, especially for larger inputs, due to redundant checks and operations. To overcome these issues, we propose an optimized solution that uses a state-based approach for parsing, which significantly improves both efficiency and clarity. The optimized approach relies on state tracking to process the source code character by character. Here, we use a Boolean variable, named in_block, to track whether we are inside a multi-line comment. This eliminates redundant operations and ensures efficiency. The steps involve initializing an empty result list to store process lines and the in_block variable to monitor the state of multi-line comments. We then iterate through each line of the source, processing it character by character. If in_block is true, we skip characters until we find the closing delimiter. Upon encountering the closing delimiter, we set in_block to false and continue parsing. For single-line comments, encountering double slashes signals the end of processing for that line. If we find the start of a multi-line comment while not in a block, we set in_block to true and skip characters until the comment ends. Non-comment characters are stored in a temporary buffer, and if we're not in a comment block at the end of the line, the buffer gets added to the result. This approach is efficient, handling edge cases like multi-line comments spanning multiple lines, and avoids unnecessary string slicing or copying operations. While slightly more complex to implement compared to brute force, it strikes an excellent balance between performance and clarity. An alternative approach involves using regular expressions to parse and remove comments. With regex, we can define patterns that match both single-line comments and multi-line comment blocks. This makes the code compact and straightforward, particularly for developers who are familiar with regex. However, regex-based solutions come with their own set of limitations. They lack flexibility in handling complex edge cases, such as nested comments or unusual formatting, and the patterns themselves can become unwieldy for such scenarios. Additionally, regex-based parsing is slightly less efficient than the state-based approach, as it may involve extra overhead in matching patterns. As a result, while regex can be a quick and concise solution, it is not ideal for this problem's requirements. After evaluating the different approaches, we chose the optimized parsing strategy with state tracking as the best solution. This approach offers a perfect balance of efficiency, clarity, and robustness. By processing each character exactly once, it ensures O(n) time complexity, where n is the total number of characters in the source. It avoids the inefficiencies of brute force, such as redundant checks and string slicing, and addresses the shortcomings of regex, such as difficulty handling edge cases. The key insight here is that the problem aligns naturally with a state machine approach. By using a Boolean variable to track whether we're inside a multi-line comment block, we can efficiently ignore irrelevant characters and focus on valid code. This method is modular, allowing for easy adjustments if more complex requirements, such as nested comments, arise in the future. Overall, it provides a clean, scalable solution that is both easy to understand and robust enough to handle the nuances of the problem. In this problem, our goal is to remove all comments from a given source code, which is represented as a list of strings. Comments in the code can be of two types: single-line comments that start with // and extend to the end of the line, or multi-line comments that begin with / and end with */, possibly spanning multiple lines. To solve this, we need to return the clean source code as a list of strings while preserving the original line breaks, just without the comments. We start by initializing three key components. First, we create an empty list called result to store the clean lines of code. Next, we use a Boolean flag, in_block, to track whether we are currently inside a multi-line comment. Finally, we use a temporary string called newLine to construct comment-free lines of code as we parse through the input. With this setup, we can begin traversing the source code line by line. If we encounter a line while a multi-line comment is already active, meaning in_block is true, we extract only the portions of the line that are outside the comment block and append those to newLine until the comment ends. This sets the foundation for the next steps of the algorithm. Now, when processing lines where in_block is false, the algorithm switches to a character-by-character parsing approach. This allows us to carefully inspect every part of the line to identify and handle comment delimiters. If we find //, we know we've encountered a single-line comment, so we can ignore everything from that point onward in the line. If we find /*, we recognize the beginning of a multi-line comment, so we set in_block to true and skip all characters until we locate the closing */. If neither of these conditions is met, the character is part of valid code and should be added to newLine. Once we finish processing all characters in a line, we check whether in_block is still false. If it is, and if newLine contains any valid code, we append newLine to the result list. At this point, we reset newLine so it's ready to handle the next line. Finally, after examining every line in the source code, the algorithm returns the result list containing all clean lines with comments removed. This systematic approach ensures we handle each type of comment appropriately while maintaining the structure of the original code. Additionally, there are several key insights and edge cases to consider. Multi-line comments, for example, can span across multiple lines, and the in_block flag is crucial for ensuring that we correctly track whether we are inside such a comment block. This is especially important for cases where multi-line comments begin on one line and end on another. The algorithm is also efficient because it parses the input character by character, focusing only on the comment delimiters without performing unnecessary operations. However, we must handle tricky edge cases, such as lines that contain both // and /*, as well as nested comments, which are invalid in most programming languages but should still be processed gracefully without breaking the code. Lines that are empty or contain no comments must also be managed appropriately to ensure the output is correct. To achieve all this, the algorithm relies on three critical data structures: the result list for storing the clean code, the newLine string for building individual lines, and the in_block boolean for tracking multi-line comments. In terms of complexity, the time complexity is O, n*m, where n is the number of lines in the source code and m is the average length of a line, as we inspect each character individually. The space complexity is O, n, which accounts for the storage of the clean lines in the result list. To better understand how the algorithm works, let's walk through an example. Suppose the input source code is as follows: source equals ina equals 0 // initialize a / multiline, comment */ int b equals 1. On the first line, we detect the // at index 12, which marks the start of a single line comment. The valid code before this point is ina equals 0, so we add it to the result list. On the second line, we encounter the /*, signaling the beginning of a multi-line comment. We set in_block to true and skip all characters in this line. Moving to the third line, we find the closing */, which ends the multi-line comment, so we set in_block back to false. The remaining valid code on this line, int b equals 1, is added to the result list. The final output is result equals ina equals 0, int b equals 1. This step-by-step process ensures that all comments are removed while preserving the structure and content of the original code. Here, we define a class named solution and implement the method removeComments, which takes a list of strings, each representing a line of code. To store the processed output, we initialize an empty list called result. Additionally, we use a buffer list to temporarily hold characters from the current line, and we introduce a Boolean variable in_block_comment to keep track of whether we are inside a block comment. The for loop iterates through each line in the source code. Inside the loop, we use a while loop to process each character of the current line. If we are not already inside a block comment, we check two cases: whether the current and next character form the start of a block comment, represented by ***, or if they form the start of a single-line comment, represented by ***. For a block comment, we set in_block_comment to true and skip the next character. For a single-line comment, we break out of the while loop, effectively ignoring the rest of the line. If neither condition is met, the character is added to the buffer, and we move to the next character. If we are inside a block comment, we check whether the current and next character form the end of the block comment, represented by ***. If so, we set in_block_comment to false and move the pointer forward. Otherwise, we simply continue iterating through the line. After processing all characters in a line, we check whether we are not inside a block comment and if the buffer contains any characters. If both conditions are true, we join the buffer into a string and append it to the result list, then clear the buffer for the next line. Finally, the method returns the result list, which contains the source code with all comments removed. This ensures the code is processed line by line, while handling both single-line and block comments appropriately. Here, we start by importing the required classes and defining the solution class, where the remove comments method is implemented. This method takes an array of strings, source, which represents the lines of code we need to process. The goal is to remove all comments from these lines and return the cleaned-up code as a list of strings. We initialize a list string called result to store the final output and a string builder called buffer to construct the current line without comments. We also define a Boolean in-block comment to track whether we are inside a block comment. The method then iterates over each line in the source array. For each line, we process it character by character using a while loop. When not inside a block comment, we check if the current position marks the start of a block comment with ***. If so, we set in-block comment to true and skip the next two characters. Similarly, we check for single-line comments indicated by ***. If we encounter one, we break out of the loop, ignoring the rest of the line. Otherwise, if there are no comments, we add the current character to the buffer and continue processing the line. Now, when we are inside a block comment, we check for its termination using the ** pattern. If we find it, we set in-block comment to false and skip the next two characters to resume processing the code. If the block comment does not end at this point, we continue iterating through the line until we locate the closing */ or reach the end of the line. After processing each line, we check if we are not inside a block comment and if the buffer contains any content. If both conditions are true, it means we have a valid line of code without comments, so we add it to the result list and clear the buffer for the next line. Finally, after processing all lines, we return the result list, which contains the cleaned-up code without any comments. This implementation ensures that both single-line and multi-line comments are handled correctly, preserving only the meaningful code. In this example, we start with a simple input that contains a single-line comment. The first step is to initialize three essential variables: result, which will store the final output lines, buffer, which temporarily holds characters for the line being processed, and in_block_comment, a flag to track whether we are inside a block comment. Now, as we process the first line, we iterate through the characters one by one. Characters from index 0 to 10 are part of the valid code, so they are added to the buffer. When we reach index 11, we encounter the // symbol, which marks the start of a single-line comment. At this point, we stop processing the rest of the line because everything after // is a comment. Since we are not in a block comment, we convert the buffer into a string and append it to the result. The result now contains the line int main. After completing the first line, the buffer is reset to prepare for the next line. Processing the second line, we append all the characters to the buffer, as there are no comments to handle in this line. Once we reach the end of the line, the buffer is converted into a string and added to the result, which now includes the second line, return 0. Again, we reset the buffer. For the third line, we repeat the same process. The single character is added to the buffer, and once the line ends, the buffer is converted to a string and appended to the result. Finally, the buffer is reset again. At this point, our final output is a cleaned version of the input, containing only the valid code, int main, return 0, and. In the second example, we deal with a block comment that spans multiple lines. Starting with the first line, all characters are added to the buffer, as there are no comments to handle. At the end of the line, the buffer content is added to the result, and the buffer is reset. The second line introduces a block comment with the / symbol at index 2. When this is encountered, we set the in_block_ comment flag to true, indicating that we are now inside a block comment. As a result, we stop processing the rest of the line and do not append the buffer to the result. The subsequent lines will now require careful handling of this block comment. While processing the third line, we skip all characters until the / symbol is encountered, marking the end of the block comment. Once the block comment ends, the in_block_ comment flag is set to false. Since no valid code was collected in the buffer while skipping characters, nothing is added to the result. Moving on to the fourth line, we add all characters to the buffer, as it contains valid code. At the end of the line, the buffer is converted to a string and appended to the result. The buffer is then reset. For the fifth and final line, we add the single character to the buffer. At the end of the line, the buffer is again converted to a string and added to the result. The final output now consists of the valid code lines, int main, return 0, and. This example introduces an edge case involving nested comments. In the first line, we process characters until we encounter the / symbol at index 13, which marks the start of a block comment. The in_block_ comment flag is set to true, and we skip all characters until the first * is found at index 31. This ends the inner block comment, and the in_block_ comment flag is set back to false. We then resume processing the remaining characters after the *. These remaining characters, which form valid code, are added to the buffer. At the end of the line, the buffer is converted to a string and added to the result, giving us the cleaned line, int main, return 0. The buffer is then reset to prepare for the next line. For the second line in this example, we simply add the single character to the buffer. As we reach the end of this line, the buffer is converted to a string and appended to the result. Finally, the buffer is reset. The final output for this example is a clean version of the input, containing only the valid code lines, int main, return 0, and. This demonstrates how the algorithm handles nested comments, ensuring that only the valid code is preserved while removing all comment content, even in complex scenarios. To analyze the time complexity of the remove comments function, we start by focusing on the outer loop. This loop iterates through each line in the source array, and if there are n lines, it executes n iterations. Next, within each iteration of the outer loop, there's an inner while loop that processes the characters of the current line. If the line has m_i characters, the inner loop processes each character exactly once in the worst case, making the complexity for processing a single line proportional to its length, or m_i. Putting it all together, the total time complexity accounts for the sum of the lengths of all lines in the source, which we denote as m. Since every character is visited at most one time, the overall time complexity becomes m. Now, let's break down the space complexity. The primary contributor is the result list, which stores the uncommented lines of code. In the worst case, every character from the input, excluding comments, is added to this list. Therefore, the space required for result is proportional to the total length of uncommented characters, or m. In addition, there's the buffer list, which holds characters temporarily while processing individual lines. At any point, the size of the buffer is limited to the length of the current line being processed, making its space complexity m_i, for a single line at a time. Lastly, the function uses a few auxiliary variables, such as in_block_ comment and I, which require constant space, or 1. Together, these components determine the overall space complexity. The total space usage is ultimately dominated by the sizes of result and buffer, which depend on the input size m. As a result, the overall space complexity is m. Now, let's consider the best, average, and worst case scenarios. In the best case, where the input contains no comments, the function simply copies all characters to the result list. Since each character is processed once, both the time and space complexities remain m. In the average case, the input contains a mix of code and comments. Despite this, the function still processes all characters, so the time complexity is still O(m), and the space complexity remains O(m) for the uncommented output. In the worst case, if the input is filled with block comments, the function has to process every character to determine the boundaries of these comments. Even under these conditions, the time complexity is O(m), and the space complexity remains O(m). Let's compare this approach to a naive solution. A naive approach might involve splitting lines and performing multiple string manipulations to remove comments. This could lead to repeated slicing or substring operations, which would increase the time complexity, potentially approaching O(m) squared in some scenarios. In contrast, the current implementation avoids such inefficiencies by processing each character exactly once, resulting in an optimal time complexity of O(m). Mathematically, the big O time complexity is justified because no nested loops or redundant operations are performed on the same characters. Similarly, the space complexity is directly proportional to the size of the uncommented code, which is at most m. This ensures that both time and space complexities are efficiently managed in the remove comments function. When solving the remove comments problem, there are several common mistakes to watch out for. First, forgetting to handle nested multi-line comments can lead to incorrect parsing. Although nested comments are rare in real-world scenarios, some interviewers might test edge cases involving them, so it's important to clarify whether your implementation needs to account for this. Next, multi-line comments that start and end on the same line are another common pitfall. For example, in the case of code/*comment*/more code, your solution should correctly strip out the comment without removing the surrounding valid code. Another area to be mindful of is preserving empty lines and line breaks in the output. Accidentally removing these can lead to formatting mismatches. Additionally, be careful not to misinterpret comment symbols within string literals. For instance, in the code system.out.println /** not a comment */ the content inside the string should remain intact. Finally, avoid inefficient parsing strategies like repeated string slicing or concatenation, as these can significantly slow down performance for large inputs. A single pass traversal is usually the best option for optimal performance. In interviews, it's important to start by clarifying the requirements. Ask the interviewer whether you need to handle nested comments, string literals, or edge cases like empty lines. This can prevent unnecessary complexity in your solution. While performance is important, interviewers often prioritize code readability and maintainability. Focus on writing clear and understandable logic to make your solution stand out. Be prepared to handle edge cases, such as comments that span multiple lines, mixed single-line and multi-line comments, and code that includes comment-like symbols within string literals. To demonstrate your testing strategy, walk through edge cases during the interview. For example, explain how your solution handles comments at the start, middle, and end of the input, as well as inputs that contain no comments. This not only shows your thoroughness but also highlights your ability to think critically about the problem. The remove comments problem shares similarities with several other problems you might encounter. The core problem itself, LeetCode 722, focuses specifically on parsing source code to strip out comments. Another related problem is LeetCode 394, decode string, which involves parsing nested structures, a skill that is conceptually similar to handling nested multi-line comments. LeetCode 20, valid parentheses, is another useful problem, as it deals with managing balanced structures like parentheses, which can help when thinking about nested comment handling. Finally, LeetCode 844, backspace string compare, is a great example of efficient string processing and modification, which aligns closely with the single-pass traversal techniques needed to solve the remove comments problem effectively. Practicing these problems can help you build a solid foundation for tackling parsing and processing challenges. There are several approaches you can use to solve the remove comments problem, each with its own trade-offs. One option is the brute force approach, where you iterate through the input line by line and character by character to identify and remove comments. This method is straightforward to implement but may not perform well for large inputs due to repeated string slicing or concatenation. A more efficient option is the state machine approach, where you track states such as being inside a single-line comment, a multi-line comment, or regular code. This approach is slightly more complex but allows you to process the input in a single pass, achieving O(n) time complexity. Another alternative is using regular expressions to directly identify and remove comments. While this method can simplify the code, it may be less flexible when handling complex scenarios like nested comments or string literals. Lastly, the two-pass approach involves first removing all multi-line comments and then handling single-line comments. This method can be easier to debug but involves additional passes over the data, making it less efficient for very large inputs. When choosing an approach, consider the trade-offs between simplicity, efficiency, and robustness. Great job following along. To summarize, we tackled the remove comments problem, focusing on parsing techniques and edge case handling. Remember, string manipulation is a key skill for many coding challenges. Keep practicing, and don't forget to like and subscribe for more insights. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!